Good morning, friends. In last we discussed about the Huygens principle, and we also discussed that according to the Huygens principle, each and every point of the particle of the wave front behave as the secondary source and emit the secondary spherical waves from it. Right? Okay, now we are going to discuss about that using the Huygens principle. What is the phenomena of refraction of the light? That means they explain the refraction of a plane wave or the refraction phenomena by the plane wave front. So this question is also asked that way, derive rules of refraction from the concept of the wave front, or explain refraction of a plane wave front from the surface separating the two medium ray to the denser. That means when the ray of light traveling from ray to the denser medium, at that time we have to explain the phenomena of refraction or derive the laws of refraction. That means the Snell's law, N1 sin I is equal to N2 sin R. We have to derive this. So for that purpose we consider this figure here. P dash is the surface separating the medium 1 ray medium and medium 2 denser medium. So we also write the answer to this question as shown in figure. Surface PP dash separating the medium 1 ray medium and medium 2 denser medium. The speed of light in medium 1 is V1 and in medium 2 is V2. Now listen here, the velocity of a light in ray medium is more than the denser medium, therefore we can add the V2 less than V1. V2 less than V1. So there is the basic introduction of this figure. Now, what is shown in the figure? A plane wave front AB traveling in the direction A dash A and incident on the interface at angle I. The plane wave front AB traveling in the direction A dash A, that is traveling in this direction, and incident on the interface at an angle I. I is the angle of incidence at which the plane wave front is incident on the interface PP dash. Now, already we know that the velocity of this plane wave front in medium 1 is V1. If the time taken by the wave front to travel the distance BC is tau, therefore BC is equal to V1 into tau. If the time taken by a wave front to travel a distance BC is tau, then BC is equal to V1 into tau. So there is the distance traveled by the plane wave front in tau time. BC is equal to V1 into tau. Okay. Now we are interested what is the shape of the refracted wave front. Therefore, to determine the shape of the refracted wave front, draw a sphere from point A of radius v2 into tau. v2 into tau. To determine the shape of refracted wavefront due a sphere of radius v2 into tau from A. Here v2 into tau is the distance traveled by refracted wavefront in time tau. Now, so this way we do this type of the sphere. Yes, we do the tangent. That means in figure the CE is the plane tangent to the sphere. Therefore, the CE is the refracted wavefront. Now, CE is plane wavefront driven from C. On the spheres. Thus, CE is refracted wavefront. There is the refracted wavefront. So there is the description of this figure. There is the incident wavefront, there is the refracted wavefront. Now we are going to derive the Snell's law. So from figure, triangle, there is the ABC, right angle triangle ABC, and triangle AEC are similar. Therefore, sin I in this triangle ABC, sin I BC upon AC. BC upon AC. What is the BC? BC is the V1 into tau. Therefore, V1 into tau upon AC. That is equation number 1. Now, for this right angle triangle AEC, we take the sine of this angle. Sin R is equal to opposite, that is the A upon AC, but A is equal to V2 into tau upon AC, equation 2. Now, taking ratio of equation 1 to 2, therefore, sin I upon sin R is equal to V1 upon V2. Now listen, here initially we make the condition is that the V2 is less than V1. V2 is less than V1. So that is our equation number 3. V2 is less than V1, that means this ratio is greater than 1. Therefore, sin I is greater than sin R. It means the angle of incidence is more than the angle of refraction. Therefore, the refracted A, or in other words, when the plane wave traveling from rare to the denser medium, so refracted wave front bends towards the normal. Therefore, R is less than I. R is less than I. Okay, we using this concept we also derive the Snell's law. Clear? Okay. Now in questioning this, in the beginning this theoretical points is describe the figure. In figure, what is that? PP dash is the surface separating the medium 1, medium 2. Medium 1 is rare medium, medium 2 is denser medium. V1 is the speed of light in medium 1, rare medium, and V2 is the speed of light in denser medium. Plane wave front AB traveling in which direction? A dash A. Incident on the surface separating the two medium at an angle I. So this angle is also I. This angle is also I. Right? Interface at angle I. If the time taken by the plane wavefront to travel the distance BC is tau, therefore BC is equal to V1 into tau. V1 is the speed of the light in medium 1 or the rare medium. Now, in second medium, the same distance, the distance traveled by the refracted wave in tau time is V2 tau. Therefore, to determine the shape of refracted wave front, do a sphere from point A of radius V2 into tau. What is the V2 into tau? Is the distance traveled by the refracted ray or the refracted wave front in denser medium. Now, CE is the plane wave front driven from the C. Actually, there is the tangent. There is the tangent on the sphere. Now, CE is the refracted wave front, and from figure, these two triangles ABC and AEC both are right angle triangle, both are similar. Therefore, sin I BC upon AC and sin R is equal to AE upon AC. Right? Now, BC is equal to V1 into tau. Therefore, sin I is equal to V1 tau upon AC and sin R is equal to V2 tau upon AC. Taking the LCM of these two equations, so we obtain sin I upon sin R is equal to V1 upon V2. So that is our equation 3. Clear? Okay. Okay, now our last third equation is sin I upon sin R is equal to V1 upon V2. Now, V1 is the speed of the light in medium 1, that means the rare medium. V2 is the speed of light in denser medium. V2 is less than V1. V2 is less than V1. And here, therefore, V1 upon V2 is greater than 1. Here, now listen. Already we make the assumption this V2 is less than V1. Therefore, sin I upon sin R is greater than 1. Therefore, I is greater than R. Therefore, reflected plane wavefront bends towards the normal. Thus, the refracted wavefront bends towards the normal. So there is the phenomena of refraction as when the ray of the light is traveling from ray to the denser medium. Here, the plane wavefront traveling from ray to the denser medium. Here again, the refracted wavefront is bent towards the normal. Now, if the speed of the light in vacuum is C, and in medium 1, that means the rare medium, is V1, then absolute refractive index of medium 1 is, that is the N1 is equal to C upon V1. N1 is equal to C upon V1. That is the equation number 4. And speed of a light in medium 2, that is the denser medium, is V2. Therefore, the effective index of medium 2 is N2 is equal to C upon V. C upon V2. Equation. Therefore, V1 upon V2 is equal to N2 upon N1. Equation number 6. By taking the ratio of equation 4 to the 5, or the 5 to the 4, we obtain N2 upon N1 is equal to V1 upon V2. Comparing equation 3 and 6. So we obtain sin I upon sin R is equal to V1 upon V2. But V1 upon V2 is equal to N2 upon N1. Therefore, N1 sin I is equal to N2 sin R. Is the Snell's law. Is the Snell's law for refraction of plane wave front. Plane wave front. So, by using the concept of the wave front, we get the Snell's law, N1 sin I is equal to N2 sin R. So here, in this part, only the mathematical terms. Already we know that what is the V1 and V2. V1 is the speed of a light in medium 1, and V2 is the speed of light in medium 2. Here we also make the assumption that in denser medium, the speed of a light is less than the speed of light in rare medium, V2 less than V1. By using this concept, this ratio is greater than 1. Therefore, sin I upon sin R also greater than 1. Therefore, I greater than R. Thus, the effective wave front bends towards the normal after the refraction. If the speed of a light in vacuum is C and in medium 1, that means in rare medium is V1, then absolute effective index of medium 1 is N1 is equal to C upon V1. Already we discussed in ray optics. And speed of the light in medium 2 is V2. That means in denser medium, the absolute effective index of medium 2 is N2 is equal to C upon V2. Now taking the ratio of 5 to 4, so we obtain the N2 upon N1 is equal to V1 upon V2. Now compare 3 and 6, so we obtain the sin I upon sin R is equal to V1 upon V2 is equal to N2 upon N1. This way, the N1 sin I is equal to N2 sin R is the Snell's law for refraction of plane wave front. Okay, now after a discussion of the refraction of a plane wave front by the interface separating the rare and denser medium. That means when the plane wave front traveling from rare to the denser medium, at the time, or in this case, we derive the equation of Snell's law. Now what's happened? If the plane wave front is traveling from denser to the rare medium, we are going to discuss this thing using the Huygens principle. Explain the refraction of the plane wave front from the ray interface, or from denser to the rare medium, or the refraction of a plane wave front at rare medium. Okay. For that purpose, is shown in the figure a plane wave front AB traveling in the direction A and incident on the surface separating the denser medium and rare medium. That means the medium 1 and medium 2. The incident wavefront AB traveling in the direction of radius and incident on the interface at angle I. Now, if the speed of light in medium 1, that is the denser medium, denser is d1, and in medium 2, that is the rare medium, is V2. Here V2 is greater than V1. V2 is greater than V1. The affected wavefront moves away from, or bends away from the normal. From the normal. After that, for certain angle of incidence, the angle of refraction becomes the 90. Such angle of incidence is known as the critical angle. For certain angle of incidence, the angle of refraction becomes 90. Such angle is known as critical angle. IC. Therefore, I is equal to IC, R is equal to 90. I is equal to 90. Now, from Snell's law, N1 sin I is equal to N2 sin R. Substitute I is equal to IC and R is equal to 90. We substitute this condition. Therefore, N1 sin IC is equal to N2 sin 90. Sin 91. Therefore, sin IC is equal to N2 upon N1. N2 upon. Thus, the affected wavefront after the refraction being away from the normal. In other words, when the plane wavefront traveling from denser to the medium, the affected wavefront moves away from the normal. Thus, if plane wavefront traveling from denser to the rare medium, the affected wavefront bend away from the normal. So that is the phenomena of refraction 4. When the plane wave front is traveling from the denser to the rare medium, we derive this equation sin IC is equal to n2 upon n1 by using the Snell's law. While in the beginning there is the introduction or what is the description of the figure. Again, plane wave front AB traveling from medium 1 denser to the medium 2 rare medium. If the speed of a plane wave front in medium 1, that means denser medium is V1, while in medium 2 rare medium is V2, V2 is greater than V1. That is our condition. The affected wave front is moves away from the normal, right? Therefore, for certain angle of incidence, the angle of refraction becomes the 90, and this angle is known as the critical angle. Therefore, the condition is that when the I is equal to IC, the I is equal to 90, and using this concept in Snell's law, we obtain the sin IC is equal to n2 upon n2. Okay, now up to this we discuss about the refraction of a plane wave front by the surface separating the two medium, either the denser to the rare or rare to the denser. Now, after that, the phenomena of refraction, we are going to discuss about the phenomena of reflection. What's happened? Using the how we explain the phenomena of reflection by using the Huygens principle. Huygens principle is that each and every point of the particle of a wave front behave as the self-secondary source and produce the secondary spherical wave, right? Therefore, how the reflection phenomena take place by using, or we can explain the phenomena of reflection by using Huygens principle. For that purpose, it's shown in the figure, a plane wave AB is incident on the reflecting surface MN at angle I. So this plane wave is reflected in the same medium at an angle R. Therefore, the speed of incident and reflected wave are same because the both waves are traveling in the same medium, and suppose there is the medium. Now, the time taken by the incident wave to travel the distance BC is tau. Therefore, BC is equal to V into tau. And the reflection of a wave takes place in the same medium. Therefore, the distance AE is also V into tau, because that is the distance traveled by the reflected wave in the same medium for time tau. Therefore, BC and AE both are equal. So first we have done this description. So as shown in figure, as shown in figure, a plane wave AB incident on a reflecting surface MN at angle I. The reflected wave is CE traveling in, just a minute. So there is the incident wave. This wave is reflected in the same medium. It is reflected in same medium as C is as C. Now, if the speed of a wave in medium is B. And tau is the time to travel a distance BC. Therefore, BC is equal to V into tau. V into tau. Now, and also AE is equal to V into tau. Because what is the AE? Is equal to distance traveled by reflected wave in time t in same medium. Okay. Now from the figure. So there is the description what's happened. AB is the plane wave. There is incident or reflecting surface MA at angle of incidence I. This wave is reflected in the same medium as CE. If the speed of a wave in medium is V and time t is the time taken by the wave AB travel the distance BC. Therefore, BC is equal to V. Similarly, AE is also the same distance traveled by the reflected wave in same time in same medium. Okay. Therefore, from figure, triangle ABC and triangle AEC are similar. Both triangles are similar. Also, the angle AEC, the ABC is angle AEC of 90. Both angle of 90. And this line AC and AC is common for both triangles. Therefore, this triangle BAC is equal to ECE. Therefore, the angle ACB, BAC is equal to I is same as the angle ACE. Angle ACE is equal to R. Therefore, I is equal to R. It means the angle of incidence and angle of refraction are same. Is the law of reflection. That means the both angle of incidence and angle of reflection are same. Okay, there is the phenomena of reflection of a plane wave by using the Huygens principle.